So welcome to mancala-bot. So what is mancala-bot? Well, typically everyone knows what a bot is, so the real question is what's mancala? Have you guys played this before?
Yep.
Yeah?
Seen it.
Okay. So it's a two-player turn-based board game. You know, think something like checkers or chess. And the board is kind of, this is an example board. A lot of times you'll see them carved out of wood. But there are other just sort of standard, more standard-looking box board games. It's a really old game. Been around for hundreds of years. And the basis of play, and I'll show you what the play looks like in just a second, to give you a little bit of a feel for it before we get into the actual mechanics of how to train a bot to play it. But essentially you have 6 buckets on each side, and the buckets will contain stones or some kind of little object to mark the playing pieces. And there are 2 buckets on the end. Those are the scoring buckets. And play goes, counterclockwise. I guess it can go either way. It doesn't really matter. But the player who controls the buckets on this side scores on this bucket, and the player who controls the top row scores on the left-hand bucket. And so this is a more digital, I guess, representation of it. I'm not going to read what's on the board. You guys can do that. But I'll describe generally what this looks like. And this is my program, actually. It was written. Hi, welcome. I'm just getting started, so I'll try to catch you guys up. Okay, so I was just explaining what I'm going to show you guys today is how I trained a computer to play Mancala, which is a 2-player turn-based board game. Something along the lines of checkers or chess. And what I'm showing now is a kind of a digital representation of the board. This is actually the program I wrote back in 2009 to play it. So, before I knew what Unity was or had any idea how to do graphics, it's all ASCII. And let me go back to the actual physical board to show you guys. The physical board looks something like this, usually carved out of wood. It has 6 buckets on each row and then 2 scoring buckets on the ends. And so here are the digital representation. Each one of the parenthetical numbers represents just a number of the bucket. And then the numbers alongside the rows here represent how many stones are in each bucket. And the object of the game is to get as many stones from the rows into your scoring bucket as possible. Well, in fact, to get just enough to get more than your opponent. I think it's called Let's Play Pokemon Go. It was a test, or it was an experiment someone set up online to allow users to input controls to a game, in this case one of the Pokemon games, in real time. And this is one of the fun little things that came out of it, which is people just spinning around in circles. In a previous iteration of this talk, I did something kind of similar to that, where I let everyone yell out sort of what moves they want to make on the Mancala board, and it wasn't that different than this. So I'm going to, instead of doing that, I'm just going to show you how the thing works. Just to, I don't know, if nothing else, prove to you that I really did this. So let me show you briefly what it looks like. And this code, believe it or not, is available on SourceForge, of all places, if anyone remembers that. It's still out there. So this is what it looks like. Again, just like a C++ application. Get through the initial menu here, and here's the board. The standard rules for Mancala are not represented here. I think the standard rules are something like 6 stones per bucket, and there are a few other nuances here, but basically the idea is on each turn I choose a bucket, 1 through 6, and whichever bucket I choose, I scoop all of the stones out of that bucket and drop 1 in each adjacent bucket until I'm done, and that's my turn. That's it. If I happen to pass my scoring bucket, I get to drop it in there. If I pass my opponent's scoring bucket, I get to skip it. At least that's how I implemented it here. There are lots of variations of rule sets for this game, but this is the way that it's implemented here. So, for instance, if on my turn, and my magnanimous AI here has decided to let me go first, I choose, let's say I just choose bucket 4. What's going to happen is, can I do this? Am I cat-like enough? I'll scoop the 4 out of this bucket, drop 1 here, 1 here, 1 in the scoring bucket, and then 1 will overflow to the opponent's side. So I'll end up with 0, 5, 5, 1, and 5, hopefully. Yeah, so something like that. And then you see the computer went ahead and chose bucket 6. So I'm going to really swiftly go through the game here, choosing buckets mostly at random, just to see what the computer does. And see, I picked a bucket with 0 stones in it, so it tells me to look again. You see he's already beating me. And there's probably no way for me to come back at this point. Yeah, I'm done. Look at that. That is actually, I'm so glad that happened. It was a total accident, but you really massacred me there. What happened was I didn't have any moves left, which is a situation that you can get yourself into. This is almost like a fool's mate, what happened here. So anyway, that's how it works. Convincing victory. Okay. Make sense? Any questions about that? Okay, so game playing AI. Well, since this was written, a lot of stuff has happened in that department. And if your news feed is anything like mine, it kind of blows up with it. Do you guys recognize any of these?
The bottom right one, yeah. I've seen the YouTube video for them.
Yeah, this is the Mar.io or whatever. And yeah, this gentleman used a neural network representation along with a genetic algorithm to teach his AI to play one of the Mario games. I think it's Super Mario World. And the way that he trained it with the genetic algorithm is really similar to the way that I trained this model. The mechanics of, like, I didn't use a neural network or anything like that. And I'm not an expert on that. I can speak to it a little bit if anybody's curious, but yeah, so that's that one. It was really fun to watch that one. If you have a moment, check it out. Do you guys recognize any of the other ones? The other ones are more along the lines of what I did.
Is that Stockfish?
Yes, Stockfish. Do you know what it is?
Yeah, chess.
It's a chess engine. It's kind of the most accessible chess engine. There's an online version. You can go on and set up your position, and it'll give you recommendations. You guys recognize any of the other ones?
Is that bottom left one IBM Watson or something?
You're really close. Wait, I think it was IBM. But you're right.
Is it Deep Blue?
Okay, yeah, it is Deep Blue. Who said that? Yeah, exactly. Deep Blue was the first computer to beat the sitting world chess champion. It was Garry Kasparov at the time, and he was no accidental champion either. I mean, he held the title for 25 years, as long as anyone. So, yeah, and this was like late 90s, early 2000s, and it was a real surprise. It was a real shock. I mean, there was a lot of effort spent on that thing, and a lot of skepticism about whether or not computers could actually do that kind of thing. And the funny thing is, it's actually, in some ways, it's exactly the kind of thing that computers are good at. We're working on now is getting computers to recognize an image of a bird, and it turns out that's a lot harder than getting it to play chess. But But yeah, so this last one, if anyone wants to take a stab at it, I'll give you a sec. It's
the AlphaGo.
It's AlphaGo, yeah, that's right. Now kind of a subsidiary of Google. It was the first chess engine to really break Go and beat the Grandmasters. And you guys familiar with Go? It's also a two-player turn-based board game. It's based with black and white stones, and I'm not an expert on it, so I won't try to get into the rules. But really interesting project because whereas the decision tree for chess branches pretty quickly, Go is just astronomically bigger. At any given stage, I mean, I think it's like a 64 by, it's like something like a 16 by 16 grid. It's huge, and at any point you can drop a stone anywhere on the grid. So just a massive, massive decision tree. So anyway, this is kind of, I didn't really set this up to be chronological, but it kind of is. A brief history of game playing AI. And like, what's the use of it? Well, I had a professor recently, like last month, who I was suggesting like, well, maybe I'll build another one of these for like an actual visual game. Maybe something like the Mario that can take a picture of the screen and try to formulate an understanding of what it's looking at and then make a decision based on that. And his response was, yeah, that's great, it's meaty enough for a project and everything, but, you know, so you teach a computer to play a game, so what? And, I mean, in some ways he's right, but I think what's happening is there's starting to be a lot of recognition that this type of learning, this type of machine learning is really valuable, not just in games, but outside of games. I mean, there's lots of actual real applications for it in medicine and every other industry, really. So for me, this is fun, and there's value in fun, really, but there's also practical application too. Okay, so let's get to the real guts of this. There are a couple of different ways to train a machine learning AI. One is the way that the Mario guy did it, which is just give it a picture, give it the same inputs you would give a human, and let it try to play and develop its own understanding of what features are important. Let it understand eventually, oh, this thing's a Goomba. Not that it's a Goomba, but this thing will kill me. Or let it understand what it means to be a gap and how to avoid it. That's not what I did here. Here what I did is I gave the computer a little bit of understanding of the features of the board ahead of time, and then I let it use those to try to determine which ones are most important as it makes its decisions. And I'll get to the, I'll do my best at explaining exactly what that means in just a moment. But so what features are important? If you're just looking at the mancala board here and trying to think about, well, what move am I going to make next? What kind of things would you consider in making your decision here? There's one obvious one.
State of the buckets.
State of the bucket, sure. And that's sort of the whole basis of this, right? In particular, which buckets are the most important?
Goals.
Yeah, the score, the current score. So that's one feature that, in fact, if I just, yeah, so score. Anything else?
Make sure you get as few of those stones on the opponent's side as possible.
Yes, and that's another feature that I included here, and I just called it, sorry, I skipped ahead here. I'll just show you all of them. I called it overflow. It's sort of how many stones are necessarily going to go to the opponent's side because, you know, I have too many in my bucket. The other one is control. That's another feature I added here. I think if I were to do this again, I wouldn't because control kind of overlaps with overflow, right? But so here's how it works. Score, obviously, in this case, Assuming that I control the bottom row, my score is 5, and that's just what I call it, 5 stones. Overflow, the way I defined it here, is how many stones are definitely going to move over to the opponent's side. And in this case, so the 2 here, yeah, I can score one of them, but the other one, there's no other choice. It has to go to the opponent's side. Same with the 3 here. At least one of them is going to go over, and the 7 is going to do the same thing. And then control is just how many stones are on my side currently at this time. Just add them all up. Okay. So those are the features. And now the next thing is for me to use those features to somehow develop a strategy. And in particular, what I want to do is place a single value on the board. So I've already got these things in terms of numbers, so I should be able to do something in order to evaluate them. And the way that I do that, I know I promised there's no math. There's not much math. There's addition, subtraction, and multiplication. I'll walk you through it. The way I do this strategy is by assigning a weight to each one of the features. In this case, I assign a weight of, and this is like on a scale of 1 to 10. So I assign 8 out of 10 to the score, 2 out of 10 to control, and 3 out of 10 to overflow. And then I just do a weighted average, essentially, something like that. I multiply the score by its weight. I multiply the, what did I call this? Control by its weight. Multiply the overflow by its weight. And then the overflow is, it counts negatively toward me because it's actually not good. The other 2 count positively. And I just add them all up and I get a number. So that's what I'm calling the value of the board for me. And the nice thing about this is that given any board, I can plug it into the computer. It can churn this thing out in nanoseconds or whatever. And so I can evaluate hundreds or thousands of boards in a really short period of time. And that's kind of the key to this whole thing. So how do I use this? Well, at any given point, if I assume that the orange blocky thing is a board position, at any given point, I'm going to have a choice to make. In the case of Mancala, I'm going to have 6 choices. In the case of this example, I'm just going to pretend that there's really only 3 choices because I couldn't fit 6 on the screen at once. But I have to make a decision about what to do. And so here's my choices. And as soon as I make each choice, each one represents giving the opponent another set of choices, right? So the opponent, in turn, for each of those 3 choices, gets his or her own 3 choices, and then on and so forth. Eventually, what I want to do is look out far enough that gives me a reasonable number of things to evaluate, and then actually evaluate them. Say, what are all the possible future states here? And so in this case, I chose to go to a depth of 3. So I'm looking 1, 2, 3 moves ahead. And if you go back to the strategy slide, I just apply the strategy, put a value on the board at that state. These are all the possible places I can get to starting here. Okay, does it make sense?
So those numbers on the bottom represent your current state of the board at that depth?
Yeah, my evaluation of the current state of the board.
Okay, so are you assuming that your opponent's always going to make a move that's going to increase their state of the board?
Yes, and you're like 1 step ahead of me. Yeah, that's exactly where we're going. So the way this, has anybody ever implemented a minimax algorithm before? Or anything like it? Yeah. So yeah, you're exactly right. This is where we're headed. So what I want to do is, I want to make my choice in such a way that I take into account the fact that my opponent is going to try to be doing the same thing, right? And so here's how it works. If I look out however far I can, in this case I'm only looking out 3 moves, I look at all the possible states from a particular decision. And in this case, assuming that this is like orange to move, and orange is trying to get the maximum score here, what I can say is that if somehow I reach this point, I'm guaranteed to be able to get an 8 on the following move, because it's my move. And so that's how I value that node, as an 8. If I somehow reach this state, who cares how I got there? If I somehow reach this state, then I'm guaranteed to be able to give myself a 6. Okay? If I were able to look a little bit farther, maybe that would be a bad choice, right? We don't know. You have to cut it off somewhere. You don't have infinite computing power, so we just cut it off wherever we can. So you see the pattern. What should I evaluate this one as? A 5. Okay, keep going. Tell me.
6.
5, 4, 9, 1, 6.
Okay, excellent. So orange, looking to maximize the value of the board, evaluates these positions as those values. Now, where the mini part comes in is, now we go up one level. Now it's blue's decision. And blue in this case is actually fighting against orange, and so wants to minimize orange's possible future states. So if blue's looking here, blue is going to say, well, if I go here, I know he's going to get an 8. If I go here, I know he's going to get a 6. And if I go here, the best he can do is a 5. So I'm going to choose this. If I somehow get here, I'm going to choose this. And so I evaluate this as a 5. Okay, does that make sense? And so using the same logic for that middle state, we're going to evaluate that as a 4. And for the final state, we're going to evaluate it as a 1. So if I can somehow force orange to get me over here, for instance, then he's in trouble. I'm going to force him down pretty low on the evaluation board. Okay, so now we're at the second to last step, and we now move to the top node, and I'm orange again. I want to maximize, so I'm going to call the value 5. So given my current strategy, the way that I currently value the board, if I look out this far and I start in that position, I now know which choice I want to make. I want to go here. Even if my opponent forces me here, I can still get myself a 5. And so according to my current strategy, if everyone plays perfectly, and that's not to say that the strategy is perfect, but given that strategy, perfect play would go through that part of the tree. Okay, does that make sense? Okay, so what do we do with this? Well, this is just one strategy. If I had a different strategy, a different set of weights for those features, they might evaluate this completely differently. And by the way, if I'm up here and I look down to this possible future state, and if any of you guys have ever played chess or checkers or something, you might see something and say, oh, there's a big juicy 9 down there. I think I'll just go that path. You forgot to account for what your opponent is going to do, and then you end up in the 1 state. So, and this is the beautiful thing about computers, is they don't forget these things. So they're always going to be making the best move, assuming that their strategy is reasonable. Okay, so as I said, that's just one strategy. What I really want to do, and this is where the kind of fun part comes in, is I want to search all possible strategies. Now in this case, that's not really possible, because if I have like a value between 1 and 10 for each of score, overflow, and control, well, assuming I'm not just using whole numbers, right? I could have 3.5 or 4.7 for any one of them. There's kind of an infinite number of possibilities to explore, and I can't have an infinite number of things play against an infinite number of things an infinite number of times in order to figure out who's the best. So I have to search. If I had a small number of things, it'd be easy to search for the best. Even with a moderate number of things, yeah, easy. Even with a moderate number of things, it's easy to kind of exhaustively go through all of them. Even for a human, but certainly for a computer. But at some point it gets too big for both humans and computers to explore everything, and so you have to have some kind of mechanism for limiting the number of things you search, but not limiting your ability to come up with a good solution. That's where a genetic algorithm comes in. Has anyone ever used one of these or seen them or implemented them before? Yeah. What did you use it for? Or did you use it or
No, I just saw it.
just familiar with it? Okay. What do you remember when you saw it? What it was used for?
There's specifically a channel that just trains AI using genetic algorithms over and over again for different games.
Is it, mostly for games? That's really cool. What's the name of it?
Is it Cobalt?
Cobalt, no. Wait, it might be it. That might be it. I like to talk about code bullet.
Yes. Okay. I'll maybe if you don't mind, stick around after, and I'll get the actual name of that.
it's
I'd like
cool.
to see it. Yeah.
I've seen it used for like antennas, like NASA uses it to find out which antennas are best at specific frequencies for satellites.
That is such a great example. There was there's something really cool that these things do, which is if you define the parameters loosely enough and let it try to design something interesting, what happens a lot of times, at least if these things are done right, the computer will find a solution that no human would ever come up with. And I think it was the example of the antenna where, you know, a lot of antenna receivers are like this hyperbolic paraboloid that, you know, any array of a radio wave coming in any incident will always sort of bounce toward the middle. But some of those examples, if I remember right, if we're thinking about the same thing, I mean, they were just like these weird looking shapes that no human ever would have designed, but they turned out to be extremely high fidelity, much better than the standard antenna. So yeah, that's a really cool example. Okay, this is not that cool, but I will show you the mechanics of how it works. So essentially, it's modeled after. I mean, it really is modeled after the real genetic process, or at least, you know, in some kind of the analogy breaks down at some point, of course, but the basics of genetics are kind of baked into this process. You know, you start with a pool of things. You have to decide which ones are more fit, and I'll show you how we do that. And those are the ones that get selected to move on to the next round. And then the ones that are fit, well, they get to reproduce, at least in a computer sense of the word. And then finally, we do introduce this idea of mutation. In most genetic algorithms, what that really means is that you do a little randomization with the features. But it really parallels exactly what happens in actual genetic mutation, which is just some random changes, random flips of some of the amino acids that form up the genetic chain. So, okay, so in mancala-bot, and how am I doing on time? I know I'm sorry we started late, and I know I'm keeping you guys a little bit late. We're about 5 minutes past now, and I'll try to make it just another 5 minutes to get through this, and then if anyone wants to stick around and ask questions, that's fine. Okay, so how do we select? Well, let's say I have a few strategies, 5 in this case. The way that I chose to do it for this this particular project was to just have each strategy play each other one in that little pool, and then use the number of wins essentially as a raffle ticket to the next round. So, for instance, there's a total of 4, 7, 8, 9, 10. There's a total of 10 wins. So the bot here who won 4 times gets a 4 in 10 chance of making it to the next round. The bot who only won once only gets a 1 in 10 chance, but everybody gets a chance. And there's a good reason for that. I'll get to it in a second. So it may be that the 3 win moves on and one of the 1 wins moves on. That happens. You roll a dice. Sometimes you get snake eyes. So what happens once they get there? Let's assume that these were the strategies behind those 2 bots. Okay? And it helps to give them a name. So let's assume that these were the names of those 2 bots. Now we get to let them reproduce, and you guys get to watch this on screen, believe it or not. Not that exciting, I promise. This is what it looks like. All I did was average the weights of the components. There are lots of different ways to choose to do this, and In fact, when you're building a machine learning model, often what you'll do is try lots of different strategies and see which one comes up with a better solution. It's often really, really bad idea in data science to sort of believe that your pet model is the right way. Really that's what I did here. Really what's better is to try out a lot of different options and just see which one's better. I just did the average here, and it did seem to work out okay. There are probably better ways to do it, but that's the choice I made here. And so once they do their crossover thing, you've now produced a new strategy, and you can use the new strategies to fight against each other again and move on, so on and so forth. The last piece of this is, okay, so I have all these things fighting against each other, and let's say I have one that becomes really dominant, like a really big fish on a small pond kind of thing. If that happens, even with the raffle system, eventually what's going to happen is this one's going to completely take over, and you're going to end up with a pool that contains a lot of guys who look like this. And you never, to kind of really, really stretch a metaphor, you never get outside of that pond. You never get to explore other options. And so the mechanism to introduce some kind of genetic variation in this sense is mutation. You just kind of perturb the weights a little bit, artificially, just randomizing. That way you don't get kind of stuck in a local maximum. And so if this guy is just an absolute beast, what we'll do is take his weights and just occasionally, or maybe frequently in the beginning, maybe frequently in the beginning and less frequently as you go on, just perturb it a little bit. Just change it up artificially. And that keeps you from getting stuck in a rut. And that's really it. So you start with some pool. I think in my case I started with a pool of about 40. Let them all fight it out. Give each one a chance to move on to the next round, cross them over, mutate a little bit, and then do that, I don't know, 1,000, 10,000, 100,000 times, however much you have computing power for. And eventually you settle in. You don't want to do it too early, but eventually you do want to settle into some kind of result. And these are the results I came up with, if anyone's curious. So after a few runs of this, and I think on the aforementioned 2001 laptop that I was using, I think I ran each one of these for about 5 or 6 days. And I think I had a pool of about 40 bot strategies playing against each other, and they played, I don't know, maybe somewhere between 1,000 and 5,000 times. And this is what I came up with. So there's some commonality here. I mean, score is very important in every sense, and that's what you would expect, right? Again, I think there's some overlap between control and overflow. So probably if I were to do this again, I would just maybe stick to just the overflow or just the control. And these were the weights that it came up with. I believe the first one is the one that you saw me get demolished by in the beginning, but the others performed pretty similarly. Okay, I think given our time constraint, I'll go ahead and cut it there, but I will be happy to stick around if anybody has any questions.